Good morning, students. In previous class, we derived the differential equation for the burning curve. It is also called the curvature equation. That is d square y by dx square is equal to ei d square y by dx square is equal to minus m, or d square y by dx square is equal to minus m by ei. This is the equation we derived in the last class. D square y by dx square is equal to minus m by ei, which is also called the curvature equation. By solving this curvature equation, we can find the slope and deflection of bending beam. That slope and deflection can be found or can be determined by three methods in this chapter. Those three methods are double integration method, Macaulay's method, and moment area method. Double integration method and moment area methods are used to find the slope and deflections when the single loads acting on the beam. If the multiple loads are there in the beam, then we go for Macaulay's method. That is the best method to solve the slope and to find the slope and deflections if the multiple loads are acting on the beam. So let us look the work examples by using the double integration first, and then by Macaulay's method, and lastly we go for moment area method. In double integration method, we solve this equation, curvature equation, by integrating twice. Then we can get the slope and deflection. But once we integrate, we get the slope, and two times integration. After two times integration, we will get the deflection equation. In this chapter, slope is represented by dy by dx or theta, and deflection is represented by y. Is that after integration, that equation, first integration, after first integration we will get the dy by dx on the left side, which is also called theta, and the second integration, after second integration we will get the y, that is a deflection. C1, C2 are the constants of integration constants. They can be found by using the boundary conditions, which can be determined. The boundary conditions are depends on type of beam or type of load. In this EI denominator, we have the EI, that is called the flexural rigidity. It is the product of modulus of elasticity, and the moment of inertia is called the flexural rigidity. Indirectly, it indicates that the strength of that section. Flexural rigidity indicates the strength of the section. Units for this flexural rigidity is newtons mm square. Flexural rigidity units newtons per mm square. EI is the flexural rigidity. These are the three methods: double integration method, moment area method, and Macaulay's method. First two methods are used for single load, whereas the third method is used for multiple loads beams. Multiple load beams. Sign conventions, already I mentioned that downward deflection is positive, upward deflection is negative, and clockwise rotation, the clockwise slope is positive, anti-clockwise slope is negative, and the distance taken from the x section, distance taken from the left end only, that is positive x direction. The distance of section x is measured positive x direction only. So this is the first work example. Concentrate on this example. It is easy to find the slope and deflection. How to find the slope and deflection in double integration method? First few problems, we will solve the problems by using double integration method. After that, we go for Macaulay's method. So let us look this problem. Simply, a cantilever beam is the cantilever beam of span L. Capital L is the length, carries a point load W at free end. carries a point load W at free end. This is a fixed end. This is the free end of the cantilever beam. Find the slope and deflections in the beam. Find the slope and deflection in the beam. That is the maximum slope and deflection. Find the maximum slope and deflection in the beam. So how to find the maximum slope and deflection at a free end? This beam is, after loading, the beam bends like this. Beam bends like this. Okay. After loading on the beam bends like this. That means that it is fixed end is free end. At free end, the deflection of the beam is maximum. The vertical displacement of the beam at a free end is maximum, and slope is also maximum at free end. If we draw the tangent after bending the curve, if you draw the tangent to this curve after bending, the tangent makes an angle of initial position is called the slope. That is the slope theta or dy by dx. This is the deflection y. So these are the maximum values at free end, and these same values are 0 at fixed end, because there is no deflection of beam at a fixed end. After loading, if you apply the load, even after load applied, the deflection at the fixed end is 0, because it is a fixed. It doesn't deflect downward direction. So deflection at this point is 0, and also if you draw the tangent at this point, fixed end, after loading, after deflection, it is coincide with the initial position. If you draw the tangent at this place, it is coincide with the initial position. So the tangent makes an angle with horizontal position is 0. So slope is also 0 at this place. After loading, if you apply the load, the beam bends like this. The slope and deflections at the fixed ends are fixed end is 0. And the slope and deflections are at a free end maximum values. This is the slope at free end. This is the deflection at free end. These are maximum at free end. Okay. This is the consider a section XX at a distance of x from the fixed end. Simply consider a one XX section at a distance of x. Okay. The XX section must be considered from the left hand support. This must be left end of the beam. So in positive x direction, this value is x. Consider an XX section at a distance of x from the fixed end. The remaining distance is L minus x. The total span of the beam is L. Clear, students? So after considering the section, you have to find the bending moment at XX section. This bending moment at XX section is M. How to find this M? So whenever you consider the XX section, you must consider the loads acting on the right side of that section. The bending moment at XX section means algebraic summation of all the moments on the right side of the section. So what are the force acting on the right side of the section? Only W, point load, is acting. Due to this point load, the bending moment will be developed at this section. So what is the bending moment due to this point load at this XX section? Load into perpendicular distance is the moment. So load into perpendicular distance is W into perpendicular distance, means this from this XX section to free end. How much distance it is? L minus x. So W into L minus x, which is in which direction? The moment will be developed in clockwise direction about the XX. Okay, if it is downward direction, it will develop the clockwise moment. If it is in upward direction, that develops anti-clockwise moment about the XX. So it is downward direction, it will be developed the clockwise moment. Therefore, clockwise moment is taken as negative on the right side of the section. It is already we studied in the second and third chapter the sign conventions of movement. Sign conventions of the bending moment is the right clockwise direction is negative, anti-clockwise direction is positive. So here I am taking negative minus W into L minus x is the movement. 1 minute. W into L minus x. W is the load, L minus X is the perpendicular distance between the section and load, and minus sign convention is represents the clockwise movement about XX. This is the bending movement at XX, since clockwise movement on right side is negative. Okay, students, let us go for the curvature equation. Already we derived the curvature equation, that is d square y by dx square is equal to minus em by ei. Otherwise, we can write this equation as ei into d square y by dx is equal to minus m. So by using that curvature equation, from the curvature equation, d square y by dx square is equal to minus m by ei. Otherwise, ei into d square y by dx square is equal to minus m. What is the m value? Already we derived that we write that the formula for the bending moment at xx is minus w into L minus x. Here in this formula, minus m is there, so minus plus w into L minus x remains. Therefore, ei into d square y by dx square is equal to w into L minus x is the required equation to solve. How to solve this equation? By integrating this equation 2 times. So by integrating the above equation, we get ei d square y by dx square integration. Ei is the constant. Integration of d square y by dx square is dy by dx. So that is equal to, on the right hand side, wl minus wx is there. WL minus WX. So WL is integration of WL with respect to X is WL into X minus WX integration W into X square by 2 plus C1 is the integration constant. Clear, students? Integration of this equation becomes WLX minus WX square by 2 plus C1. Constant integration is constant into X. If it is X is there, X square by 2 is the integration. Therefore, W into X is there minus W into X minus W into X integration X square by 2 plus integration constant C1. So by integrating once again the equation, by integration this equation, we will get the slope deflection equation. This is the slope equation with, in terms of constants and X. And by integrating again, once again the above equation, we will get the deflection equation, that is ei into y. After integration, ei is the constant, integration of dy by dx is y, that is equal to, what is the integration of wlx? Wl into x square by 2 minus w into x square integration x cube by 3. So x cube by 6 it becomes w into x cube by 6 plus C1 into X. C1 is the constant integration C1X plus second integration constant is C. So this is the solving method in double integration method for the given curvature equation. Okay, students, this is the curvature equation. After solving, that is after integration, we will get the slope in first integration, and we will get the deflection equation of the other after the 2 times integration of curvature equation. Okay, these are the 2 equations. In these 2 equations, C1, C2 are the integration constants which can be determined by the following boundary conditions. What are the boundary conditions for the given cantilever beam? For the cantilever beam, wherever the cantilever beam is given, for that cantilever beam, these are the boundary conditions. These are the fixed boundary conditions. Boundary conditions means at x is equal to 0. What is at x is equal to 0? X is equal to 0 means we are taking x from the fixed end. If this x is equal to 0, where this xx consider? If x is equal to 0, the section becomes at fixed end. Section if we consider the section at fixed end, the x value is 0. Okay, at a fixed end, x is equal to 0 means at a fixed end. X is equal to L means at a free end. If we consider this section at a free end, the x becomes L. L minus x is 0. L minus x is 0, x becomes L if we consider the section at free end. If the same section consider at fixed end, then x value is 0. That means if whenever x is equal to 0, that end is fixed end. Whenever the x is equal to L, that is a free end. Okay. In this case, the boundary conditions for this cantilever beam is x is equal to 0. If x is equal to 0, what are the parameters 0 at the fixed end? Now itself I explained that at a fixed end, the slope value 0 and also deflection is also 0. If we apply the load, the beam doesn't deflect at fixed end, and also the slope at the fixed end is 0 after deflection. So those are the two boundary conditions. First boundary condition, at x is equal to 0, dy by dx is equal to 0. That means x is equal to 0 means at x is equal to 0 means fixed end. That means at fixed end, slope is 0, dy by dx is 0 or theta 0. Since at the fixed end, slope is 0. Second boundary condition is at x is equal to 0. Again at the fixed end, deflection also 0. So y0 at x is equal to 0, y0. These are the two boundary conditions generally we will take for the cantilever beam. These are called the boundary conditions. So after applying these two boundary conditions into our derived slope and deflection equations, then we will get the constants C1, C2. So upon substitution of first boundary condition, in which equation we can substitute this boundary condition? This boundary condition can be substituted in the slope equation only, because we know the slope condition at a fixed end. Slope is 0 at fixed end. Therefore, whenever we substitute the x value as 0, there the dy by dx is also 0. So dy by dx equation is this. This is the slope equation, which is called the slope equation in terms of C1. By eliminating the C1, we will get the final slope equation. So how to eliminate the C1? By substitute the x value 0 on the right hand side, then dy by dx is 0 on the left hand side. So left hand side dy by dx is there. Substitute in place of dy by dx 0 value, then we will get the 0 on the left side, 0 into ei. So 0. That is equal to, in place of x also 0. So wl into 0, 0 minus w into 0 square by 0, 0. So only remains on the right side is C1. So C1 is equal to value 0. So C1 value is 0. From the first boundary condition, C1 value is 0. And by substituting the second boundary condition into the deflection equation here, ei y equal to WLX square by 2 minus WX cube by 6 plus C1x plus C2 is the deflection equation in terms of constants. So by substituting the x is equal to 0, wherever the x 0, the y is also 0. So on left hand side 0 value, ei into y value 0 kabatti ei into 0. Substitute in place of x 0. And these three parameters are 0. In these three parameters, x is there. When we substitute the x value 0, these three parameters 0. The remains value is C2. C2 is the remaining value on the right side. So left hand side 0, right hand side only C2. Therefore, C2 is also 0 by using the second boundary condition. From the second boundary condition, we can say that C2 value also 0. So from these two boundary conditions, from the boundary condition 1, C1 0, from the boundary condition 2, C2 also 0. So after eliminating the C1, C2, we can write the slope and deflections. These are the slope including C1. This is the deflection including C1, C2. So C1, C2 value is 0. Therefore, we can replace the C1 as 0. So remaining equation is slope equation. If we substitute the C1, C2 values, 0 values, we will get the remaining equation as deflection equation. So final slope and deflection equation after eliminating the constants, after replacing the constants, slope equation is ei dy by dx is equal to WLX minus WX square by 2. Already we written is WLX minus WX square by 2. C1 value 0 kabatti మనం రాయట్లేదు. Okay, and deflection equation eiy equal to WLX square by 2 minus WX cube by 6 plus 0. C1 0, C2 0 kabatti ఈ వాల్యూ మనం రాయాలి. సో రిమైనింగ్ ఈక్వేషన్ మన డిఫ్లెక్షన్ ఈక్వేషన్ అవుతుంది. సో eiy equal to WLX square by 2 minus W into X cube by 6. These are the slope and final slope and deflection equations. By these two slope and deflection equations, we can find the slope and deflection at every point of the beam. ఈ రెండు ఈక్వేషన్స్ యూజ్ చేసుకొని మనము ఎక్కడైనా బీమ్ లో ఎక్కడైనా స్లోప్ అండ్ డిఫ్లెక్షన్ ఫైండ్ చేయొచ్చు బై సబ్స్టిట్యూటింగ్ ద x వాల్యూస్. x వేరీస్ ఫ్రమ్ 0 to l. x అనేది 0 నుండి l వరకు వేరీ అవుతుంది. ఎక్కడైనా 0 నుండి l, between 0 to l, we can find the slope and deflections after bending the beam. So here maximum slope find చేయమంటారు. Maximum slope ఎక్కడ ఉంటుంది? In cantilever beam always the maximum slope at free end. Free end దగ్గర maximum slope ఉంటుంది, and also maximum deflection కూడా free end దగ్గర ఉంటుంది. So maximum slope in the beam occurs at free end, that is at x is equal to l. Free end దగ్గర x value ఎంత? Free end దగ్గర x value ఎంత? Free end అంటే ఇక్కడ, free end అంటే ఇక్కడ x value ఎంత? X becomes l. సో x l అయినప్పుడు ఫ్రీ ఎండ్ అవుతుంది, x 0 అయితే ఫిక్స్డ్ ఎండ్ అవుతుంది. ఆల్రెడీ బౌండరీ కండిషన్స్ x is equal 0 దగ్గర సబ్స్టిట్యూట్ చేసాం. ఇక్కడ మనం అడిగింది ఏంటంటే ఫ్రీ ఎండ్ దగ్గర ఇండైరెక్ట్ గా స్లోప్ అండ్ డిఫ్లెక్షన్ అడిగాడు. మాక్సిమం స్లోప్ అండ్ డిఫ్లెక్షన్, ఫైండ్ ద మాక్సిమం స్లోప్ అండ్ డిఫ్లెక్షన్ ఇన్ ద బీమ్. సో మాక్సిమం స్లోప్ అండ్ డిఫ్లెక్షన్ ఎక్కడ ఉంటుంది అంటే ఫ్రీ ఎండ్ దగ్గర ఉంటుంది. బికాస్ ఆఫ్టర్ డిఫ్లెక్షన్ the vertical displacement of end point is more and slope is also at the end point is high. The tangent makes an angle of theta with respect to initial position is maximum at free end. Therefore slope and deflections are maximum at free end. At free end x value is l. So by substituting the derived slope and deflection equations in place of x, l, then we can get the slope and deflections at the free end, that is the maximum slope and deflections. Wherever the problem in the problem, wherever the asking the slope and deflection, we can find the slope and deflection by substituting the x values. Okay, ఎక్కడైనా మన బీమ్ లో మనం ఫైండ్ చేసుకోవచ్చు ఈ రెండు ఈక్వేషన్స్ యూజ్ చేసి స్లోప్ అండ్ డిఫ్లెక్షన్స్. క్లియర్ స్టూడెంట్స్? I hope you understand how to solve that curvature equation for the cantilever beam and how to substitute the boundary conditions, how to write the final slope and deflection equations after eliminating the constant of integration values. So after getting ikkada variki matram prati problem ki same procedure, if slope and deflection derived formula variki every problem ki same procedure, wherever it is, whatever it is, cantilever beam or simply supported beam, whatever the beam given in the problem, the procedure for the solving the curvature equation is same up to this. From this we can find the slope and deflection at asking place, that is the wherever the he asked in the problem the slope and deflection, we can find the slope and deflections at that particular point by substituting x values. So in this problem maximum slope at free end kabatti free end దగ్గర x value l ఉంటుంది. So by substituting the x in place of x l value, then we can get the slope. If you substitute the x place l in deflection equation, we will get the deflection at the free end. So first మనం ei, this equation, slope equation, ei into dy by dx is there. Ei into theta is also we can write, dy by dx is also right theta value. So ei theta actually. If you substitute in place of xl, then we can write it as maximum theta. So whenever the x value l, the theta is maximum. That's why I am written here ei theta maximum in place of ei dy by dx. Dy by dx can be replaced by theta. So both are same. Theta means slope of the curve. Dy by dx is also slope. So ei theta, if we find the maximum slope, you should find in place of x l value. Here I am substituted the x value as l. So w into wl into l minus w into l square by 2. So it is x square by 2 is there. I am substituting l value l square by 2. So wl square minus wl square by 2. So wl square minus wl square by 2 is wl square by 2 itself. So wl square by 2 is equal to ei theta maximum. Therefore theta maximum can be write as from the above equation wl square by 2i. This is the formula to calculate the slope, maximum slope at the free end in the cantilever beam with a point load. W is the point load, L is the span of the beam, E is the Young's modulus of the given material of the beam, I is the moment of inertia of the given section of the beam. Okay, this is the maximum slope in the beam. Let us find the maximum deflection similarly. Maximum deflection. So also maximum deflection in the beam occurs at the free end. Maximum deflection in the beam occurs at the free end. That is at x is equal to again L. X is equal to again we take L. So this L value, substitute this L value in place of x L value in deflection equation. So EI y maximum is equal to, whenever we write the y maximum, we should substitute in place of x value L. So EI y maximum is equal to WL into L square by 2. This is the WL into x square by 2 is there in place of x, and I replace the x value as L. So WL into L square by 2 minus W into, in place of x cube by 6 is there in slope equation. I replace that x with L value, therefore W into L cube by 6. So L6 is the LCM. From this above equation, 6 is the LCM. So 3WL cube, this is a WL cube. 3WL cube minus WL cube, it will becomes 3WL cube minus WL cube is 2WL cube by 6. 2WL cube by 6 is becomes WL cube by 3. Okay, from this equation we can write EI y maximum is equal to WL cube by 3, or y maximum is equal to WL cube by 3 EI. This is the equation or formula to calculate the maximum deflection of the cantilever beam if the point load acting at free end. Okay, these are the formulas we derived for cantilever with point load. Okay students, maximum slope and maximum deflection ekkada develop avutayi? Free end దగ్గర maximum slope and deflections will be developed due to point load at free end. We are finding the maximum slope and deflection at free end by substituting x place, by substituting the L value in place of x. Clear students? Let us go for the second problem. Same cantilever beam but not point load here. The UDL is acting on the point on the beam. Look at this diagram. A cantilever beam of span L, that is the total length of the beam is L, carries a uniformly distributed load of small w per unit length over the entire span of the beam. Find the slope and deflections at the free end of the beam. So here also we are going to find the slope and deflection at the free end of the beam. So at the free end means x place lo L substitute chestam. At the fixed end means in place of x we are substituting 0 value. If x is equal to 0, then it becomes the fixed end. If x is equal to L, it is the free end. So we are taking x value from the fixed end. We are taking a section at a distance of x from the fixed end. Clear students? Let us go to the solution for the same procedure. Same procedure we follow that. Consider a xx section at a distance of x from the fixed end. First we చేయాల్సింది ఏంటంటే beam ఇచ్చిన వెంటనే ఇక్కడ xx section consider చేయాలి. ఎంత distance లో we consider at a distance of x. So bending moment at xx is, we must find before proceeding the problem bending moment at that particular xx. How to find the bending moment at xx? M value. So whenever we consider the section at this place, we must consider the forces, the movement, all the movements of the forces on the right side of the section, So how much distance it is? This total distance is L, and the remaining distance on the right side is L minus x. This is the L minus x distance. So the UDL value is on the right side, occupies the length of L minus x distance. So UDL value is W, which occupies the length of L minus x. Therefore, it is per unit length. W is the given per unit length. The total load acting on the right side is W into L minus x is the total load. So W into L minus x, small w, L minus x is the total load acting on the right side of the section. So where it acts generally, It acts at the center of gravity of that rectangular load. It is also called the rectangular load or UDL. It is the total load concentrated at the center of gravity of the load. So therefore, the distance of that concentrated load from the section is becomes L minus x by 2, because total distance on the right side is L minus x. Therefore, it is the L minus x by 2. Total distance from the section to B is L minus x. The load which is on the right side is concentrated at a distance of L minus x by 2. So load is W into L minus x. Distance is L minus x by 2. Therefore, load W into L minus x into distance is L minus x by 2 is the distance. So this is the movement, bending movement at xx. Bending movement at xx. Okay, ఇది ఏ డైరెక్షన్ లో యాక్ట్ అవుతుంది? It is always on the downward direction. It will be develop the clockwise movement at xx. It will be developed in the clockwise movement at xx. Therefore, we can take it as minus clockwise movement. Clear, students? Minus w into L minus x into L minus x by 2. So it becomes minus w into L minus x whole square by 2. L minus x whole square by 2. So I written here m is equal to minus w into L minus x into L minus x by 2 is the distance. So minus w into L minus x whole square by 2 is the bending moment at xx. After getting the bending moment at xx, we substitute the bending moment value in the curvature equation. So from the curvature equation, what is the curvature equation? Ei d square y by dx square is equal to minus m. This m is the bending moment at xx. So bending moment xx is minus w into L minus x square by 2. By substituting this minus w into L minus x whole square by 2 in place of m, then minus minus cancels. Already the equation having the minus and also m having the minus sign, minus minus plus. So ei d square y by dx is equal to w into L minus x whole square by 2. Clear, students? This is the equation to solve for the slope and deflections. So this is the equation to solve by solving this equation. How to solve this equation? So by rewriting that equation, above equation, ei d square y by dx square is equal to ei d square y by dx square is equal to w by 2 is there, w by 2 into, it can be write as a minus b whole square formula. So L square plus x square minus 2lx. So after rewriting the above equation, we can integrate. By integrating the above equation integrate chestam. By integrating the above equation, we will get on the right and left hand side, ei is the constant, integration of d square y by dx square is the dy by dx. For every problem, this is a procedure, constant procedure. By finding the first, we have to consider the xx section in the given beam, find the bending moment at xx, and substitute that bending moment value into the curvature equation, then integrate 2 times. Upon integration of once, we will get the slope equation. On integration of second time, then we will get the deflection equation. So after integrating first time, ei into dy by dx is equal to w by 2 is the constant, integration of L square is with respect to x, L square x plus x square integration x cube by 3 minus 2lx integration 2l into x square by 2. 2 to cancel, lx square remains. So minus lx square plus c1 is the integration constant. Already you know that mathematics, how to integrate the equations and how to write the constant of integrations. So by integrating once again, we'll get, upon integration, this equation once again, left hand side becomes ei into y. Integration of dy by dx is equal to y. So ei into y equal to w by 2 is the constant, integration of L square x. X is there, integration of x is x square by 2. So L square x square by 2 becomes plus x cube by 3 integration is x square x power 4 by 12. So x power 4 by 4 is there, 4 into 3 is 12 in the denominator. So x power 4 by 12 minus Lx square integration L into x cube by 3. So L x cube by 3. plus C1 integration C1x plus C2 is the second integration constants. So after integrating this equation, we will get the slope and deflection equation including the constants, integration constants. So similarly, in the previous case, we will get the integration constant by substituting the boundary conditions. So boundary conditions are same for cantilever for every problem. C1, C2 are the integration constants which can be determined by the following boundary conditions. At x is equal to 0, slope is 0, dy by dx 0. At x is equal to 0, deflection is also 0. These are the fixed boundary conditions for cantilever beam. Cantilever beam is these are the two boundary conditions. You have to remember that. At a fixed end, both slope and deflections are 0. At fixed end, x value is 0. Okay. So by substituting these two values into our equation, we will get C1, C2 values at 0 as in the previous case. So from the first boundary condition, slope value. From the first boundary condition, ఎందులో substitute చేయాలి? dy by dx 0 కాబట్టి ఫస్ట్ స్లోప్ ఈక్వేషన్ లో సబ్స్టిట్యూట్ చేసుకుంటాం. dy by dx 0 సబ్స్టిట్యూట్ చేసినప్పుడు x వాల్యూ కూడా 0 సబ్స్టిట్యూట్ చేయాలి. సో x 0 అయినప్పుడు ఈ 3 పారామీటర్స్ 0నే. 0 into w by 2 0. So c1 is the remains on the right side, 0 on the left side. So c1 value 0. And at x is equal to 0, y is also 0. By substituting the second boundary condition into deflection equation where the y is 0, x value 0. So left hand side y 0 substitute చేస్తే left hand side 0 అవుతుంది. Right hand side లో ఎక్కడైతే x ఉందో x place లో 0 substitute చేయండి. Including c1x also 0. So all the three parameters and fourth parameter c1x is also 0. Therefore the remaining value on the right side is c2. So c2 is equal to 0. These are the C1, C2 values are 0 by substituting the boundary conditions. Okay. Okay, students. Therefore, slope equation, final slope equation is EI dy by dx w by 2 into L square x plus x cube by 3 minus L x square. How to get this equation? Already we derived this equation including C1. This is the equation. I rewrite there. EI dy by dx is equal to w by 2 into L square x plus x cube by 3 minus L x square plus C1 value is 0. So after eliminating the constant value, we can get the slope equation and deflection equations. Here C1, C2 0 and not write C1, C2 values here. So after eliminating the C1, C2, we'll get the slope and deflection equations. EI dy by dx is the slope, EIy is the deflection equation. In that slope is the dy by dx, in this y is the deflection. So after getting the final slope and deflection equations, we can find the slope and deflections at every way of the beam. So in this problem, the slope and deflection asked at the free end. At the free end, the x value is L. At the free end, x value is L. If you want to find the slope and deflections at center of the beam, then x becomes L by 2. At the center of the beam, x value L by 2. At fixed end, x is equal to 0. At free end, x value L. So slope at the free end means at x is equal to L. By substituting the x value as L, we will get the slope at the free end. So it is a slope in place of x, substitute L value, then we can get the theta at a free end. Free end is B. Your free end is B. Fixed end is A. Free end is B. So we will get the slope at the point B. That's why I'm written here at B. EI theta B. EI into dy by dx and the theta B రాస్తున్నాను. Whenever we write the theta B value, we will substitute. We should substitute in place of x L value. So after substituting w by 2 into L square into x place lo L substitute cheste, it becomes L cube plus x place lo L substitute cheste L cube by 3 minus again L cube. In place of x, L substitute cheste L into L square L cube. So L cube cancel, remaining value L cube by 3. So W L cube by 6 it becomes. So EI theta B equal to W L cube by 6. Otherwise theta B equal to W L cube by 6 EI is the formula to find the slope at a free end. In this, W is the URL, uniformly distributed load per unit length. L is the length of the beam. E is the Young's modulus. I is the moment of inertia for the given section. So this is the formula to calculate the slope at free end and the deflection at free end. Deflection at free end, that means at x is equal to L. At free end, x value L. So by substituting the x value L in deflection equation, we will get EIT YB. YB means deflection at free end. Whenever we write the YB, substitute x value L. So after substituting in x value L in deflection equation, what is the deflection equation? EIY equal to W by 2. In place of x, if we write the x value L, we can write EIYB equal to W by 2 into L power 4 by 2 plus L power 4 by 12 plus L power 4 by 3. It becomes, here I written L power 4 by 2, L power 4 by 12 minus L power 4 by 3. So the LCM for this is 12. So it becomes 6L power 4 plus L power 4 minus 4L power 4. 3 4 is 4, 4L power 4. So 6 minus 6 plus 1, 7L power 4 minus 4L power 4, 3L power 4. So 3L power 4 by 12. W by 2 into 3L power 4 by 12. Otherwise 3 4s are 12. 4 into 2, 8. So WL power 4 by 8. Finally, we will get the deflection at the free end is YB equal to WL power 4 by 8. EI is the formula for the deflection. Clear, students? So these are the formulas to calculate a slope and deflection at the free end. Like this, you have to solve that given curvature equation and substitute the boundary conditions, and we will get the slope and deflection at every point of the beam. We can find the slope and deflection at every point of the beam by using final slope and deflection equations. Okay, in the next class, we'll go for third problem, that is the cantilever with UVL.